Hello, welcome back to our YouTube channel, my dear friends. Hope everyone is doing fine from your end. Please kindly take care of your health. Once again, and also I thank everyone, those who are subscribed to my YouTube channel, ADC Max. Thanks for your constant support. Please kindly watch our YouTube channel because your support only make me to upload more videos and very interesting videos. In this video, I am going to use the third one among the method to determine the inverse Z transform is residue method. I really amazing because among the other possible methods, this is the one and only method which gives the answer directly without any the background of the Z transform results. I don't know about the Z transforms, but I can get the answer with the help of this residue theorems. Because I made a separate videos how to determine the inverse Z transform by using the convolution theorem or maybe the power series or long division method or method of partial fractions. Even though those methods we need some Z transform ideas, but in this problem, in this method, we don't want to any idea about the Z transform. We can get the answer very directly with the help of the Cauchy's residue theorem. So let us see what is the Cauchy's residue theorem. This comes under the complex integration. I made a separate video how to evaluate the complex integrations with the help of the Cauchy's residue theorem. Actually, the Cauchy's residue theorem says that we can find out the function phi of z is be analytic. When we say that the function is analytic, a function is differentiable at the point z is equal to z0 and also at each and every point of its neighborhood. Then we say that the function is analytic. Suppose each and every point inside the neighborhood of z0 is differentiable, it has a differential derivatives, then we say that the function is called analytic. That's the first terminology I am using, the analytic function. It is also called as a regular function. It is also known as holomorphic function. But sometimes at the point z is equal to z0 or z equal to a, the function is not analytic. Then we say that the function is called singular point. Then we say that the point is called the singular point, and at this point the function fails the analyticity. It fails the analyticity, means it is not analytic at that point. So once in the neighborhood of the point z0, this is the one and only singular point, then this is called the isolated singular point. One and only. When we expand this phi of z as the Taylor series expansion, then we will get it is sigma n is equal to 0 to infinity an into z minus a whole power n plus sigma n is equal to 0 to infinity bn by z minus a whole power n. This is called the positive powers of z at the point a, that's the point, positive powers of n, this is the negative powers of z minus a. And this negative powers of z minus a is called the principal part of the Lorentz expansion of the phi of z about the point z equal to. Now once the point is isolated singular point, when we are going to express phi of z as the Lorentz expansion, particularly this principal part, it can be designed what type of this singular point. Suppose there is no principal part, that means there is no negative powers of z minus a, then we say that the singular point is called removable singular point. It's called removable because it will remove certain terms in the Lorentz expansion at the point is equal to a. Suppose if there are finite number of terms in the negative powers of z minus a, when we are going to express as the Lorentz expansion in the principal part, then it is called the poles. Right? Suppose if there are an infinite number of terms in the negative powers of z minus a power n, this is called the principal part, then it is called the essential singularity. So the singular points can be categorized in 3 types. I made separate video, please go and watch the types of singularities. Okay. Now poles. So suppose if this is my simple closed curve C, and there are finite number of poles, z1, z2, etc., zn, and now my question is, what is the integral over the curve C for the function f of z dz? It is nothing but 2 pi I into sum of the residues of f of z inside the C. Because these points are called poles. Poles means singular points. At that point, the function is not analytic. So this is called the Cauchy's residue theorem. The same concept I am going to use to determine the inverse Z transform. Okay. So I made separate video for this one. Please go and watch it. I'm not coming back to the inverse Z transform. Now I am going to use the Cauchy's residue theorem. So Cauchy's residue theorem is nothing but Z inverse of x of z equal to x of n. This is my requirement. The inverse Z transform of x of z is nothing but sum of the residues of x of z into z power n minus 1 at each of its poles. So what's the poles? Poles means it is singular point. It has a finite number of negative powers of z. So that's called a pole. Now how to determine the residue of the x of z power n minus 1 at the poles? Now the poles depends upon its order. Suppose the order is n, this is the formula, 1 minus n minus 1 factorial. Differentiate with respect to z n minus 1 times. Order n means n minus 1 times differentiation. Z minus a whole power n into the x of z power n minus 1. So this is the formula to determine the residue. Right? Suppose the order is 1, it is called the simple pole. Order is 1. If n equal to 1 in the first formula, I get the second formula. Put n equal to 1 minus 1, 0 factorial is 1. So there is no differentiation. So z minus a whole power n into x of z power n. So this is the formula to determine the residue of f of z at the poles. The pole order 1 means it's called simple pole. More than order 1 means use the first formula. That's it. Right? Now I am going to take the first question. So find the inverse Z transform of. So to see that, the question is find the Z inverse of, yes, Z by Z minus 1 and Z minus 2. Z minus 1 and Z minus 2. Z minus 1 and Z minus 2. Suppose maybe the question given like this, find the Z inverse of Z by Z squared minus 3Z plus 2. Yeah, I think if it is given like this, we can split up into 2 linear factors. Now my first idea is, so this is my x of z, right? This is my x of z or this is my x of z. Now when I take the Z inverse, I need to get the x of n. So this time I am going to use the residue theorem. If I take x of z is equal to, so what's x of z here? X of z is equal to z by z minus 1 into z minus 2. Yeah. So the poles of x of z are, given by, it is completely given by the denominator equal to 0. So what's the denominator here? Z minus 1 into z minus 2 is equal to 0. Z minus 1 into z minus 2 equal to 0. By the way, z equal to 1 comma 2. What is the order? Order is nothing but how many times it repeated? Only one time. So it is called the simple pole. It is called the simple pole. Am I right? It is called the simple pole. It's clear. Now, once we got the poles and its order, go for the residue. Now find out the residue of x of z into z power n minus 1 at the first pole, z equal to 1. So I am going to use the second formula in the place of a equal to 1. Right? So this is equal to limit z tends to 1 because a equal to 1. Z minus 1 into x of z by, use the factor form because of we can cancel the corresponding pole terms. into z to the power n minus 1. Is right? Now see that the corresponding pole term will cancel naturally. Then let us multiply this z power 1 into z power n minus 1. We will get limit z tends to 1 z power n by z minus 2. Now substitute z is equal to 1 in this place. What we will get is 1 power n by 1 minus 2, otherwise minus of 1 power n. Is right? So this is the residue of x of z into z power n minus 1 at the pole z equal to 1. Similarly, to determine the second pole, residue of x of z at the pole z is equal to 2 of order 1. So limit z tends to 2, z minus 2 into x of z by z minus 1 into z minus 2 into z power n minus 1. So once again, the corresponding z minus 2 will cancel. The pole term will cancel. By combining this z into z power n minus 1, so we get limit z tends to 2, z power 1 into z power n minus 1 is nothing but z power n, right? By z minus 1. Let us substitute z equal to 2, we get it is 2 power n, the numerator, denominator is 2 minus 1, 2 minus 1 is 1, so this is the answer 2 power n. So by Cauchy's residue theorem, by the residue theorem, what is the technique? The technique is to determine the residue value, and by the theorem what says that the z inverse of x of z, yeah, in this case x of z is z by z minus 1 to z minus 2 is equal to the required sequence x of n is equal to sum of the residues. So sum of the residues here, so residues of x of z into z power n minus 1 at the pole z is equal to 1 plus residue of x of z into z power n minus 1 at the pole z is equal to 2. So now substitute here, what is that? Minus of 1 power n plus 2 to the power n, otherwise 2 to the power n minus 1, because 1 power n equal to 0, 1, 2, 3, what is 1 only. So this is the direct answer. So this is the one of the best method what I have strongly recommend you to that. To determine the inverse Z transform, the residue method is one of the easiest and the best method, because the other methods like method of partial fraction or conversion theorem or even the long division method, we should know some standard Z transform results and as well as the generalize the terms to get the x of n. But here no such things we are going to use. Once we found the poles and the corresponding the residual values, just summing up all the residual values which will give the inverse Z transform of the given x of z. So I hope everyone is understand. Some more problems I make a separate video. Please kindly go to watch. Thank you. Signing off. This is your ADC. Thank you. Take care. Bye.